Hello, welcome everyone. My name is Daniel Checa. Today we're going to talk about a project I've been working in the last 2 or maybe 3 years. A huge project called Arndt Compositions. It has some connections with Fibonacci numbers. We're going to talk about statistics and generalizations of this combinatorics object. So let's begin. This is the context of this presentation. We're going to introduce this concept. If you are not familiarized with compositions, it's fine. We're going to discuss a little bit about new identity for Fibonacci numbers. This is very interesting. We're going to talk some statistics that may arise for this subject, as well as some generalizations. And the ending, we're going to talk about palindromic Arndt compositions. Okay, so let's begin. Maybe you don't know this, but basically integer compositions are different ways in which I can describe a number as sum of other positive numbers. Okay, this only works for positive numbers, of course, and for positive integers. Okay, so they're basically sequences. I'm gonna call the sum of this sequence the size, and the number of summands I use, I call them parts or summands. Okay, so for example, it's very well known that the number of compositions for every number n is 2 to the n minus 1. So for example, the number 4 has 8 compositions, and are those here. Okay, so 4 can be written as 4 or t plus 1 or 1 plus 3 or 2 plus 2 and so on. These are all compositions or 4, and notice here order matters. Okay, so what is an Arndt composition? We are gonna add another restriction in the sequences. Of course, there are integer compositions, but there is another condition, and it is that the summands in the odd positions must be greater than the summands in the next even position. Basically, the first summand is greater than the second one, the third summand is greater than the fourth one, the fifth summand is greater than the sixth one, and so on. Okay, and if a composition, for example, has an odd number of parts, well, that is fine for the last summand. We'll say that this condition is backwardsly true. Okay, so this is just notation. We're gonna define a sub n as the set of our compositions for every n, an as its counting sequence, and capital N as the union of these sets. Okay, this is just notation. Don't worry. So let's see a example. 7 can be written 64 ways. There are 64 compositions of 7, but only 13 of them are compositions. And let's check. In these cases, the first one is greater than the second one. The third one, in the case of these compositions, doesn't matter. It's backwardsly true for the last summand. And for example, for these ones, the first summand is greater than the second one. The third summand is greater than the fourth one, and so on. And I think there's a little, there's one more. Okay, first one greater than the second, and so on. Okay, so there are 13. And if you list, let me explain something just before the counting sequence. It's very natural to represent these compositions as bar graphs. Okay, every time you have a composition, for example, of this number, you can write the first summand as a column, and the next summand as another column, and so on. Okay, that will be very important in these proofs. So if you list these compositions for every n, you notice that, for example, for 7 there were 13. Okay, so basically you have the sequence, and if maybe you notice, this sequence is possibly the Fibonacci numbers. Okay, so is it? And well, I haven't told you, but why the name? Well, of course, this mathematician George Arndt published in the OEIs that these sequences were counted by the Fibonacci numbers, but he didn't told us an improvement in 2013. In 2022, these two mathematicians, Hopkins and Tanguy, proved that these numbers are indeed Fibonacci numbers. Okay, so yes, that's fine. So what I did in my thesis project and in some following articles, my goal was to present some alternative proofs by using generating functions, power series, and this is advantageous in the sense that it allows you to study some statistics and generalizations concerning this object. Okay, I invite you to read this. This is my thesis. If you want to read it, it's online, and it's very interesting what we can find there. Okay, so today I'm just gonna talk about the best parts. Here, as I said, I'm gonna talk about about the creme de la creme. Okay, the best of the best, just the best results. So let's go for it. Okay, so we have introduced this. Okay, so the very first part we're gonna talk about a new identity for Fibonacci numbers. Well, where does this identity comes from? Well, I'm gonna talk to you about how can we enumerate these Arndt compositions without generating functions. Let's let A of C be the generating function of this object. This is just notation. A sub O will be the generating function of those that have an odd number of parts, and A sub B an even number of parts. Okay, this is just notation. So as you may notice, as I told you, the last summand in an Arndt composition doesn't matter actually. You can put anything there because the restriction just holds between pairs of summands. So if you have an Arndt composition with an odd number of parts, you can decompose it as an Arndt composition with an even number of parts, as an object in the A sub B, concatenated with a last summand that can be anything. Okay, and in the case of an even Arndt composition of even length, okay, we can decompose it as this. We can decompose it as an odd Arndt composition, and we can add squares here in the last summand, and here in the penultimate summand and in the last summand. So we can preserve that difference. Okay, so we always have that this summand in an odd position is greater than the next summand in an even position. Okay, so we can translate this into generative functions, and we obtain this functional system, and this is very simple to solve, and we have this solution for AC. Notice that this is the generative function of the Fibonacci numbers. This is well known, so this is a proof. So another way to tell this is that maybe I want to find the generative function of Arndt compositions for a given length, for a given number of parts. So I call this BK of C, this generative function, and as we proved just earlier, we can decompose B of C for any K as this, for any odd number or even number. Okay, so if you proceed inductively, you may prove that we can prove that BK of C has this formula. Okay, so this is very important because from this you can derive an explicit formula for Arndt compositions that have a specific number of parts. So this context sequence will be the Arndt compositions of N that has that have K summands, exactly K summands. Okay, so this first identity I proved in my thesis when I did I derived the article with my thesis advisor, Jose Luis Ramirez. He liked it kind of this more is pretty much the same. We can proceed differently, but it's pretty much the same. Okay, he didn't like the negative part here. Okay, but that's fine. That's pretty fine. So let's think about this. If we add this sequence for all k by fixing n, you will recover the Fibonacci numbers, right? That's pretty simple. So we will have a new identities for Fibonacci numbers, and here they are. these are new identities for Fibonacci numbers. Well, as far as I know, nobody knows any combinatorial interpretation for this identity, so I invite you to think about this. But this is one of the most beautiful results also in my thesis. Well, let's talk about some other statistics just a little bit. I'll study the size of the last summand, the size of the first summand. The most important results there are new combinatorial interpretations for the moments, for the first moment of the distribution of those sequences. For that, I mean, what will happen if you sum the last part of every Arndt composition for a fixed n. So you have this formula here and this formula here, and these are indexed in the OIIs, but these are simpler combinatorial interpretations. So this is very important. I also studied some statistics in the bar graph of Arndt composition. For example, here the area will be the number of squares. There are 33. The perimeter, well, you can count it. It's 38, and the 0 points are 15. You can count it here, okay? So there's also a formula for that. It's nice. I mean, I like it, but it looks well bigger. Okay, it has this rogue expression. So I proved this in 2023, and this is a way to remember this. And of course, this is related to Pick's theorem, because I mean, if you are if you know about this. This is related to counting interior points and area, and this has something to do with Pick's theorem, and it has something special here when you can relate this to the first and second moment of this distribution. So maybe you can read it in my thesis, okay, or in the articles. Okay, some generalizations that may arise for this object. What will happen if you modify this the initial constraint, the initial inequality, by adding up a k in the right hand side, or maybe you can add it in the left hand side, but it's pretty much the same if you talk about any k. Okay, what will happen if you just consider the absolute difference between these pairs of summands for any k? Okay, that'll be something interesting. What will happen if instead you multiply some number in the right hand side or the left hand side of this inequality? That it's also interesting. It's pretty much solved in my thesis. And also, well, what happens if we just don't consider descending tuples, descending pairs of summands? But what happens if we consider 3 or 4, right? Like 3 going down and next 3 going down. Well, that has something to do with partitions that doesn't share any common summands. So you can concatenate this and obtain you can obtain some interesting formulas here, but this has been studied. I'm not gonna talk too much about this, but it's pretty much by decomposing this in the last summand is pretty much that. In 2025, we published an article with Jose Luis and Nati and about the restrictions on the set of possible parts. What happens if you consider in the parts to be, for example, odd or even or maybe any set? Okay, so that may be interesting. What about if you restrict the number of parts to be, for example, just consider even number of parts, or just parts multiple? I mean, a number of parts multiple of 3, for example. That'll be also interesting. We consider the colored version of this object is very common in compositions or in combinatorial number theory to consider the colored versions of these things. It has nice results. And well, I want to talk at this moment about another one that we did in the article, that are palindromic Arndt compositions. This can be done by standard methods, but this has something really interesting. A palindromic Arndt composition will be adding another restriction, and that will be that this composition will be symmetric in some points. Okay, you can read it the same forward and backward. For example, the palindromic Arndt compositions of 11 are those. And to enumerate these compositions, this will be the condition, okay, formally, explicitly, and we will denote them by PA, okay. So also, since the middle summands cannot be simultaneously satisfy both conditions, the number of parts cannot be even. We cannot have two summands equal in the middle, so that doesn't make sense. The number of parts of polynomial compositions must be odd. The second summand must be between two adjacent greater summands, since when you reflect it, that must be translated, that inequality must also be translated to the other side. So you have like compositions going starting from up, down, until you reach the middle part of that composition, and then you reflect that initial part. So the very first part of your composition will seem like this, okay? The very first parts. These compositions are known, I think, as down-up compositions, as I saw in the OAIs. So let's know them by W. So we're gonna use something called the adding a new slice method. This is, for example, known when you count Carlit's compositions, and it was valued by Sedgwick, but no, I'm sorry, by Prodinger, as I remember, and Flageolet. Okay, so let us examine first the even case. Well, this is just notation again, but basically the very first thing that we must do in the even case for these compositions, for the going down up compositions, is that you may add pairs of summands. Okay, so here I may change the variables. Now X counts the weight of the composition, C counts the size of the last summand, and Y counts the number of parts. Change a little bit, but it's pretty much the same. So every time you have a last summand, maybe you have to think about how do we add the next blocks. So in the case of the weight, you may consider the last one summand to be greater than the previous one, okay? And the next one, the last summand, must be less than, okay? So you may consider this into this substitution, and what we do is to substitute this into the previous coefficients, as I define it here. This a sub k of xc, okay? This counts, he says, this is the general function of those compositions in W with 2k summands, okay? So when you solve this functional system, I won't explain too much about the details, but you can read it in our last article. You have this. It's pretty simple from the same argument to develop a formula for the odd case, and then you can think about palindromic compositions in two cases where the middle summand is greater than the adjacent ones, or is less than. Okay, so when you split this, you have to do two substitutions in considering if the parts to the left and the right must be even or odd, okay, the number of parts. And well, to reflect it, we can put this here. You can change x to x squared and y squared to reflect that part. Okay, so that will be. Here you find the palindromic compositions that are congruent to 1 modulo 4, and these ones are congruent to 3 modulo 4. Okay, so those are the only two cases. And when you add these two cases, you may find you can find this result. This is the general function for palindromic compositions. And well, let's just do an example. If you take the coefficient in x to the 11, this is it, and of course this matches what we found earlier of the compositions of 11. Okay, so well, another thing that is interesting is that you can isolate the dominant poles of this function. So for this from standard methods, you can find the the asymptotic formula for this sequence. This is much easier than just taking the coefficient into this generative function, of course. So, well, that's it. I hope you enjoyed this. That's all, folks, and I hope you to see you next year. I hope. I don't know. So these are the references, and well, that's it. Goodbye.